results in this nice workshop. So I'll talk a bit about the Kitaev model. So it's nice that Mariana talked before me. So she discussed a bit magnetism, a bit topology. So I'll show how these concepts appear in the context of the Kitaev model. Oops, apparently it's not working. So first, I would like to acknowledge my collaborators. So I've been doing lots of work in the Kitaev model with my collaboration in Dresden, Matthias Voigt and Lucas Jansen. And then there is the work I'm going to show, the work done in my group here in Brazil with 2 master's students, Pedro, which was with me in São Carlos, now in Dresden, and Vitor, which just moved to Minneapolis. So those are the reference. This is the works I will be presenting here. I also would like to thank the Brazilian agency, CNPq and FAPES for the support for doing this work. Okay, so let me start. So before moving to the Kitaev model, I'll just briefly talk about frustrated magnetism. So just since this is a broad audience, so to people understand what I'm interested at. So this is more or less, so this is a diagram. Here's U, like the Hubbard U. And this is the axis I will call frustration. So I'll discuss this a bit more. So as we saw earlier in Mariana's talk, so if you increase U, you localize your electrons, you go to the Mott insulated limit, and generally you have an ordered state, like an antiferromagnet order. But what's nice, so if now you have like this frustration, so if you increase frustration in some way, so then you can essentially move away from this ordered state to a spin liquid state. Okay, so spin liquid state would be a state with no magnetic order and several other nice properties which I'll discuss. And these are just show let's say two lattices which are very famous. One is the triangular lattice, which you do find order, but there is a region around the transition which in principle can find carrier spin liquids, and the Kagomel lattice where you indeed do not find long-range magnetic order. So those are 2 famous examples in 2D. So this is what I mean by frustration. So generally you require some odd loops with antiferromagnetic interaction between the spins. So you always end up with this question, how should I put this blue spin up or down? Because either way, leave one spin unsatisfied. On the triangular lattice, there is a way out. You have form a non-collinear order. But if the frustration is strong enough, you really destroy long-range order. And you go into this spin liquid state, which basically the first experimental signature is absence of spin freezing, so you do not see ordering down to very low temperatures. Theta here is like the Curie-Weiss temperature, is just an energy scale in your problem, which is nice. The spin liquid state, you usually have fractional excitation, which means the low energy excitation are not magnons. For instance, they can be spinons or Majorana fermions, as I'll show in this. So this is something interesting. Usually, you have topological order. So this is what makes this system special, because you do find topology in an interactive system. So this is nice. And for instance, if you are gapped, if you have a gapped spin liquid, you have a really nice result in 2D. You can calculate, for instance, the entanglement entropy. There is a correction to the area law, which is topological entropy, which uniquely characterizes your ground state. So this is just to show how rich the systems can be. So this is, I'll highlight some of these nice properties in the simple Kitaev model. So this is the Kitaev model. So this it was essentially proposed like 20 years ago by Kitaev. So it's shown here. It's like an easy model, but there is a peculiarity that, let's say, you pick up a honeycomb lattice, you have 3 bonds. So let's say you call this the Y bond. Along the Y bond, only the Y components of the spin interact. Along the Z bond, only the Z component interact, and along this X bond, only the Z X component of the spin interact. So you have like 3 copies of the IZ model, so, and the direction of the interaction of the spin is attached to the bond. So in principle, you already see a key ingredient to this bond is a strong spin-orbit coupling. So this is kind of material which will eventually show this kind of Heisenberg, this kind of Kitaev model. So this is a nice, it seems a bit artificial, but I'll show you it's not. And it's interesting because you have an exact solution. So you have a construction we should call parton constructions. Basically, you just break your spin into parts. So that's the name, parton construction. In this particular example, I'll just represent my spins in terms of Majorana fermions. Okay, so just introduce 4 Majorana fermions, which are represented by these colored dots here. So we have red, green, and blue. So, and this, you basically pair up these Majoranas along these bonds. So, and there's one single Majorana fermion which is left over here. So by the end of the day, you map your spin Hamiltonian into a tight bind Hamiltonian of Majoranas hopping in this honeycomb lattice. And this map is exact for this model, okay? So this is interesting. So and we know how to solve this problem. We know this from graphene. So it's like kind of, you just have half graphene because you have Majoranas, so it's kind of half fermions. So it's, you have the Dirac cone, so, but you just have, let's say, the positive energy value. So just because it's Majorana. But it's nice, so you have a spin system, no long-range order, because, I mean, this is fermions, no order at all. And your excitation are not Magnus, are Majorana fermions. So this is an example, perfect example of a spin liquid in 2 dimensions, and it's exactly soluble. This is you can vary this constant kappa, you can get a full phase diagram, but I'm just focused on this B phase where Kx equal to Ky and Kz, and we indeed have this Dirac cones as the dispersion of a Majorana. But that's not the full story. That cannot be the complete story because there is another part. When you fractionalize the spins, you always have to take care of some constraints and basically introduce some flux configuration or gauge configuration. I'll just say fluxes. So basically, you have to fix this quantity WP here, which is just the flux around this plaquette, which is basically the product of all these spins around the plaquette. Okay, so this you have to do in order to make this map complete. Okay, this is a technical issue, but it's really important, and that's what comes fractionalization. You break up your spins into Majorana and fluxes. So that's why it's interesting. That's where fractionalization comes. And what makes the model soluble is that these fluxes in this particular model, they are static. So basically, you just fix your flux configuration, you solve your problem. This is an exact solution. Your job is to find which flux configuration gives the lower energy. Okay, so that's essentially how it works. And then basically, this flux can have 2 values. It can either be +1 or -1. The ground state for the clean models when the flux are all equal to +1 state, which you call 0 flux, which means no flux at all. So in this here, just to highlight how interesting the model is, this is the structure factor at Q equals 0 as a function of frequency, so it's the dynamic structure factor, and you see it has a gap here, so this gap is basically this flux gap. So basically, in order to generate a spin excitation, you have to pay the flux gap, and then the Majoranas come into play. So it shows up in observable, so that's where fractionalization comes into play. And also, there's another interesting aspect of this model, topological aspect. If you apply a magnetic field, let's say, perpendicular to the plane of the honeycomb lattice, which you call 1-1 direction, you produce you gap out the Dirac cone, so generate a mass. So okay, this is basically proportional to the product of these fields. And you end up with the model. It's really similar to the Haldane model. So now in the language of the Majorana fermions, you put a second near hopping, but this is directional hopping indicated by these arrows here. So this is basically a topological insulator. So you really generate chiral Majorana edge modes. Okay, so in your system, as soon as you turn on the field. The difference here is because you are an insulator, what you measure is not the Hall conductivity, but actually the thermal Hall conductivity. So you have to apply a gradient of temperature and measure the thermal Hall effect, and it will have this form here, which is precisely what to expect. And this factor half here is the quantization value, and it's half instead of 1 because you have a Majorana. It's like half a fermion, okay? But this is an interesting prediction of the simple model. And as I promised to you, this is not completely abstract, although it's interesting from the theory point of view. But like since 2009, Jacqueline and Caliulio, they proposed a mechanism by which you could generate these Kitaev-like couplings in real materials. So this is somehow what made the field come really alive, and it's interesting. So basically, the ingredients you need to have, as I said, you need a Mott insulator, but with strong spin orbit coupling. So those are the 2 ingredients. So generally, we look into iridium, so D4 and D5 elements, instead of the D3, which we are more used to. So and basically, you have these iridates, which are shown here, the lithium iridate, and this is one of our hydrogen lithium iridate, which I'll talk about. And also, there's this famous one, which is alpha ruthenium trichloride. So basically, these kind of materials, they show, at least they have some Kitaev term, but that's not the full story. But those are the materials which in principle could look into this kind of Kitaev physics, and they are known as Kitaev materials. So in principle, this model, it finds realization in nature. So, but what often happens is that you have more than Kitaev. So let me just highlight some results on the alpha rutino trichloride here. So this is a material. It's essentially van der Waals materials, honeycomb lattice, which are coupled by van der Waals. So really almost decoupled planes. So, and then what happens is the following. So this is the magnetic field, but let's just look at this axis here. So if you load the temperature below a certain EL temperature, your system will order, so you show long-range magnetic order, and in particular, you show the zigzag order. So I highlight how the spins are arranged here. They form the zigzag pattern. So the system does have order. So it means it cannot be fully Kitaev. It has more terms because it orders. Kitaev won't order with just Kitaev. But what's interesting, if you apply a magnetic field, so you melt the zigzag order, and then if the field is high enough, you go into the, let's say, the polarized phase, where all spins essentially point in the direction of the field. But there's an intermediate phase here, experimental at least, where they find inside this dome a topological signature. How do they see it? Well, they measure precisely the thermal Hall effect. So this is what I'm showing here as a function of the field. Okay, so this is essentially what I'm showing. So if you are at small field, you are in the ordered phase, they are not quantized. But if you go into this intermediate region, you find a kind of plateau here if you have good eyes. I mean, this is still, it's not completely clear how clear is the signature, but still, this at least strongly supports the idea that this material indeed has realization of the Kitaev spin liquid, but you need to crank up the field because, I mean, you need to kill essentially the zigzag phase. So, and that motivated us to study models beyond the Kitaev model. That's why I told you I would like to perturb the Kitaev model. So I basically present two ways which we did this. So first way we did it, really we have the usual Kitaev term, and by hand we just put a Heisenberg term. So this is the kind of term which you expect to be present in real materials. So and then one can study this so-called Heisenberg-Kitaev model. So it has the Kitaev term and plus the J term. And also there, I'll apply the field because the field is interesting. But let me just focus first on the phase diagram of JK. So you can parameterize J and K by an angle. So this angle phi here. So basically when phi is equal to pi over 2 and 3 pi over 2, you are in the Kitaev limit, and you see that the liquid phase, it survives some value of J, so it's stable to some extent. But if you increase J, then you have ordered phasing, or have 4 different ordered phasing, and also this, in particular the zigzag phase, which the experimental ground states contain this model. Okay, but the point I want to make here is that the liquids phase, they indeed are stable. So in principle, they survive a finite J. So this is interesting. And also, so this was known already. What we did, it was basically repeat this study, use exact diagonalization for a small cluster, 24 spins, but now applying a field. Okay, so now we apply a magnetic field. So basically, we cut this phase diagram, and now you verify along the x-axis, and the y-axis we put the field. So there are several phases. I won't be discussing them. There is a long and nice history behind all these phases. What I would like you to focus on more on these dots, which are the exact diagonalization. The phases are from nonlinear spin wave theory. We can discuss them later. There are other references, but I do not have time to go through them here. So what is interesting is that there are two things I would like to point out here. First, when you turn up the field, what happens is that the fluxes, they become mobile. They're no longer static. So, I mean, you have to resort to some approximation or numerical calculation. So the fluxes get dynamic, so it's hard. You lose integrability of the model. That's why you resort to this exact diagonalization. And first thing what happens is because this Kitaev term is highly anisotropic, when you apply a field, the ordered phase, the general what happens, they can't. So the spins, they tend towards the field, and then you get to the polarized phase. So, but because this Kitaev term is highly anisotropic, you will get what we call anisotropic Kant. So the Kant angle of all your spins inside the magnetic unit cell, they can in principle be different. So this is interesting. For this particular field direction, which is what I call 001, it's not that interesting. You just get the phases which you have without the field, but you see when you change the field direction, this complicated energy evolution leads to really interesting states. So just to point out this nice fact, but let us just focus here first. So here you see the extent of the Kitaev spin liquid. It depends whether Kitaev is antiferro or ferro, so you see it's different. And also, if you apply a field, you see the antiferromagnetic side is much more robust with respect to the field, so the liquid survives. Whereas if you apply a field in the ferromagnetic Kitaev model, essentially the spin liquid is immediately destroyed. So there is a strong anisotropy between these two. Okay? And also it's interesting because now this model is anisotropic. So if you change the field direction, change the physics. Okay? So there is no SU2 symmetry here. So I apply a field along the so-called 1-1 direction, which will be perpendicular to the plane if you like. As I promised, there are several new phases. I won't be discussing them. Let us just focus on really on the Kitaev spin liquid here. So if you increase the field, you see it's still stable. There is a new phase here, an intermediate phase. And then, essentially, you go to the polarized phase. Okay, but there is an intermediate phase here. So this was essentially discovered like 4 or 5 years ago. So the Kitaev term has a second spin liquid, well, at least a putative spin liquid, let's say, which is this intermediate phase. So you start with the Kitaev spin liquid, increase the field. You have this disordered phase here, which is compatible with the U1 quantum spin liquid, but that does not matter much. But there is in principle another spin liquid phase, and then you go to the polarized phase. So this is a really interesting model. What's nice, there are two features to highlight. Again, if you are close to the ferromagnetic side, this phase does not appear, just when you are here. And also you see this kind of phase here. It seems it goes to a tricritical point here when it merges with the ordered phase and the polarized phase. So it's kind of, there should be a appears to be a tricritical quantum critical point here, which is interesting, but I mean, so far it's just numerics on a small system, you cannot say much. And also, in principle, if you are brave enough, you can say that you can somehow capture a bit of the experimental situation, because I mean, this purple phase here would be the zigzag phase. You melt it, you enter into the spin liquid phase, then you get this intermediate phase, then you go to the polarized phase. So in principle, it's possible for you to melt the ordered phase and get the Kitaev spin liquid. So although this is not contained in the simple Kitaev model, in the extended Kitaev model, you could get this, let's say, this descriptor. So, but that does not mean, I not claim these explained experiments, but just show to you, if you extend the Kitaev model, in principle, you can at least produce a robust scenario to explain the experimental results. So this is essentially what I would like to talk about on this part. Now, I'll in the last like 12 minutes of my talk, I'll talk about these different iridate, which essentially have hydrogen. So basically, your people are able to build these iridates with lithium and sodium, and then try with nitrogen, but nitrogen is tricky because it's too light. So generally what happens, you end up with a nice system, but with lots of disorders. So that's basically the tale I'd like to share with you. So those are the experimental results. So basically, this is the reference to 2008 Nature here. So I'm just showing here, this is the specific heat divided by temperature as a function of temperature, both on log scales. And it's nice because this is the result. So if you do not have an external field, basically the specific heat diverges as a power law, essentially as a square one of the square root of T. So this is the experimental result. If you apply a field, you quench this divergence. Okay? The same divergence you see on the susceptibility, which is magnetization over field. So the divergence is again compatible with this power law, and it's quenched if you apply a field. And also if you locally, you can measure the NMR relaxation rate, and you see basically this 1 over T1T basically saturates at low T. This means essentially you have lots of, it's like Coringa law essentially, so which is again, you expect for a metal, but not for an insulator. So this is strange. It's telling you they have lots of low energy excitations in your system. So that's essentially the model, and how I'd like to treat this. So our claim will start with the Kitaev spin liquid, but now we perturb this with disorder. Okay, so that's essentially how we perturb this. This again, it's an old story. There is also, it also may be relevant to iridium doped alpha routine trichloride. Okay, so that's basically our motivation. So again, now I'll take a different approach. Instead of really start with the microscopic model, I'll start with the Kitaev model already in the Majorana representation, so that would be the original Kitaev model. These use here are basically the value of the link value, the link variable, so this U is equal plus or minus 1, it's basically controlling my flux sector. This kappa term here is precisely that term which breaks time reversal symmetry and makes it will mimic the external magnetic field. So this is the term which I alluded before. It's a next nearest neighbor hopping, but it's directional. And also you can include a term here which now has its third neighbor, so it's shown here. So this kind of strange third neighbor, but you have to follow the Manhattan distance essentially. This term preserves time reversal symmetry. Unfortunately, I do not have much time to discuss it, but you can see by the form of the Hamiltonian, basically what I'm doing, I'm just writing an effect theory. So I keep the integrability and write all possible terms which can appear in your system. So this is a nice program, which is reasonably controlled. And the idea is I can include generally the terms which are even, they break time reversal symmetry, and the odd terms they do not break. And I still consider static fluxes because I need to retain the integrability. So I know I can solve the model at least on a computer because it's still not interacting. So essentially that's the part of the game we're playing. And I can calculate the topological invariant, so to characterize the topology, the chiral Majorana edge states in the system. Instead of general, we calculate the Chern number. Here I calculate this both index, which is equivalent, but it's more convenient to do in real space. It's just a matter of convenience. But I show here the both index as a function of this kappa, which will be the external field. And you see that it's -1 if kappa is negative and +1, so it's really quantized, and it changes sign with the field. And of course, it does not depend in K3 because K3 respects time reversal symmetry. Okay, so but that's essentially that just to show the both index, it's a good topological index. And what we did, well, consider several different kinds of disorder. I'll just show you vacancies. Basically, what to do is just extract spins and dilute your system. So that's what we do. So here I'm showing let's say, the honeycomb lattice, and I just remove this spin. So now this is the vacancy. To make this a bit more controlled, I dilute the same number of spins on the A lattice and B sublattice. Okay, this is just to simplify our life and to avoid trivial zero energy modes. Because if you unbalance, you have trivial zero energy modes, which I would like to avoid. And then we can generate essentially two kinds of spins. We have the paired spins, which are, let's say, this spin here, which has all the neighbors, and also have unpaired spins, which are spins which are missing one neighbor precisely because this guy was diluted. So we have these two kinds of spins. They are interesting. I'll come back to them in a moment. And what we do, we again do a variation of flux configuration. So we propose different fluxes for a system and see which one minimizes the energy. So that's the approach. The zero flux would be the old fluxes, which means all these blue bonds here means that U variable is 1. And also have this bound flux. This bound flux is an interesting state. It was essentially discovered in this earlier work here or impurities in Kitaev model. And people realize that the impurity tends to bind a flux. So if you remove an impurity here, it will bind a flux inside this L equals 12 plaquette. So this is actually the ground state of the system, which essentially means you have to flip one of the link variables here. So this is actually called the bound flux because the vacancy binds a flux to it. So it's kind of interesting state. And we do this variationally, so this is the ground state energy divided by the Kitaev coupling as a function of dilution. And you really see that this is a different state, random flux, which you call random flux, which does not have a good energy. You see the zero flux and the bound flux is really close in energy, but the bound flux is indeed smaller. So this is really the ground state. I mean, people realize this for a single for a single vacancy, and it's true for a finite fraction. And also I defined something which I call the two flux state. Basically, as I told you, when you flip a bond, which means you flip the spins in the bond, beside of Majorana excitation, you get this flux excitation. Basically, I just flip this link variable. So I create two fluxes, because if I flip one bond, I create two flux and the neighboring plaquettes. And then I define this gap as the difference in energy of the system with one bond flipped with regard to the original system. So that I define this 2F, which would be the gap, the flux gap. And then I can calculate this quantity as a function of x. You see, well, it diminishes with x, so, but still does not change much. That would be the value of x equals 0. But it's interesting, if you have an unpaired spin, the flux gap is 0 just because you do not have a neighbor to flip. So it's trivially 0. So this spin is interesting because this is going to be important. So these unpaired spins, they do not have to pay the flux price to excitate them. So now you see how the story is evolving. And that's how we interpret. So in the simple model, we interpret this set of divergence as some sort of Griffiths-like singularities. So how come Griffiths phase came here? So let me just go through it in 1 or 2 minutes. So this is the density of states of a Majorana excitations. This is the energy, okay? And then you see some, so this is the energy. So you see at low energy, you start to pile up some energy, some states, okay? And this is, if you go to high value of dilution, like 6% and 8%, if you put this on a log-log scale, you really can fit this to a power law. So it's showing you, if you dilute enough, your density of states has a pile-up of low-energy states, which follow more or less a power law. And this is consistent with what you see in the experiment. So the vacancies are really introduced zero-energy states in a power law fashion. And it's interesting, this translates immediately into the specific heat, but we can really calculate the susceptibility for the Kitaev model within an approximation. And you really see you have two contributions, essentially. You have the bulk the paired spins, they contribute, they have a constant, they give a constant contribution, Pauli-like, if you wish, which is essentially inversely proportional to that two flux gap. But if you go to low enough temperatures, these unpaired spins, they are the one contribute with the singular, they give a singular contribution, simply because they do not have to pay the flux gap, they just have to pay the Majorana gap, and the Majorana has this power law divergence. So it really appears here. So it's kind of, in the sense, that's why I call Griffith. And you can play the same game with the NMR, and you really see it saturates at low temperature. So this is interesting because if you put vacancies in the Kitaev model, you get like a power law divergence of the singular thermodynamics, which you can associate with these unpaired spins. And this is kind of, you can understand in a Griffiths-like phase, but there is no critical point here. It's just you are in a phase which is essentially critical already. So that's how it comes about. We can produce Griffiths-like arguments. I mean, how can we generate a power law distribution of density of states? Well, we can do the usual argument. So let's pick up a region where you have, let's say, you put vacancies on all its surroundings. So the probability of finding such a red region is exponentially small in its perimeter because you dilute along its boundary. So, and then you can just pick up, let's say, a small system size with open boundary conditions and calculate the gap of the first excitation, because if the system is small, there's overlap between the localized states and the edge. This generates a gap, so you can calculate how this gap evolves with the system size. Well, it also goes exponentially with the system size. So, as usual, this exponential cancels that one, and we end up with the power law. Okay, I just mentioned this is not the true asymptotic regime, and this is known for, at least for if you have a particle hole symmetry, the asymptotic law form, you can prove analytically is this, but it's really hard to see this numerically, okay? This is really low temperature, which you cannot access for easily access numerically, but this is the result if you have particle hole symmetry, which is not always the case in our problem here. This is well known from the graphene studies. But at least it looks like this kind of Griffiths-like or power law behavior is like an intermediate crossover regime, which is relevant, at least seems to be relevant to the experiments. And just to finish 1 minute, so there is an interesting aspect. We can calculate also, beside the thermodynamics, calculate this both index and as a function, again, of the dilution, okay, for different parameters. And you see there's a difference if you consider zero flux and bound flux. For zero flux, for small x, it's spin to 1, but it deviates. We believe this is more, it has to do with finite size effects. But I mean, if you go to bound flux, you really see it spin to 1. It deviates, but look at this. I mean, this is really small scale. So it looks like it's really pinned, okay, so the bound flux. So it looks like in this simple model, there's an interesting physics here. So you dilute, although you generate some zero energy modes, you can still keep the topological index quantized. And this is, I mean, why is that so? So one thing, it should happen, your gap, say your non-interacting, your clean gap should be stable. So what you realize is the following. So this is the density of states, again, for the bound flux. When you start to put vacancies, you generate a new state here inside the gap. So this is, and all, let's say, the flux, the vacancy states, they come, instead of just filling up the gap, they come for this state here. There's an in-gap state which somehow protects, which are localized states which protect the topological gap. It's interesting and keeps your index quantized. We can more or less understand, well, we can understand this if you just do two vacancies. Basically, we realize because the vacancy binds a flux, it generates a state which lives in its neighbor but has a finite energy. Whereas if you have zero flux, the energy of this state is really zero. So basically, if you have zero flux, you fill a gap. But if you have a bound flux, you really, I mean, because you bind the flux, this protects your clean gap. And this is really interesting. That's why the both index remains quantized. So I'll just leave with my conclusions. So we just talk to you. And I just want to point out, I mean, if people could do experiments, which is hard, thermal experiments, in principle, these Majorana chiral modes could survive dilution, which is interesting. So in principle, you could find there was this question before. At least for this simple model, we expect that the topology would survive disorder. But important here is the fact that you have interacting systems. So because of the flux binding, it's actually what protects the system. Thank you very much.
Thank you, Eric. Do you have questions?
I have two questions. So one, do you have any numerical results including gamma interactions? Or do you have any,
sorry?
Like gamma interactions?
Oh, that's a good question. No, I mean, we are thinking like this gamma interaction would be contained into this K3 term, for instance, but we didn't do, let's say, the exact map. So you could do this, but I mean, just think like this gamma term is being mimicked by this. But no, we didn't do explicitly this microscope. But in principle, it can be done. We know how it looks like in terms of this effective models.
And for the exact diagonalization?
The exact diagonalization you can do, but we didn't do the gamma term. We just do the JK model, just because here our goal was really to see how, let's say, the regional phase diagram was modified by the field. But in principle, it can be done with the gamma term. Okay. Yes, sure.
And then I didn't understand this part about the Bott index. So if this K prime term preserves time reversal symmetry?
Yes.
For upper equals 0, the gap would be still closed, right?
Yeah. So, I mean, I'm just saying we can consider this K3 prime term. There is also the K3 term. Those are in principle terms which are allowed by symmetry you can put in the system, and they preserve time reversal, so they do not induce topological phase. And in principle, they mimic like the gamma term, the J term. So that would be. So that's our idea. And the Bott index, what I just said, that the Bott index, they depend on kappa, so it breaks time reversal. So it's either plus or minus 1, but it does not depend on K3 prime. Okay. Just a trivial statement here. Okay. But I didn't explore too much the K3 prime just because of lack of time. Okay. But this is just a trivial statement.
Okay, thank you.
Nice talk. Thank you. About this Bott index, what is it? You said it's connected or related to the chair number, but it's not exactly to the chair number. No. And is there a bulk boundary correspondence?
And that's a good question. So the simple answer is no. So it's kind of, the problem is it's a topological index which calculates in real space. So it's kind of not easy to see the bulk boundary correspondence, but in principle, it just measures the singularity of a matrix. So for simple case, you can prove it works, but these here are just using numerically. It is consistent, but there is no definitive proof. I mean, this will work always, but I mean, at least for all tests, it does, okay? So it's not easy to calculate this even in simple examples. I mean, there are some papers by Hastings, I mean, he shows in simple examples, but I mean, in general case, it's not proven.
So there are no topological edge states which
No, there are. I can show there is. I'm just saying that it's not obvious to calculate like in a simple model, to calculate the churn number. I mean, you see in the topological phase, you can really calculate. Here, the bad thing is generally you need to do this numerically, so it's hard to find an analytical example, but I mean, there are a few. But there are edge states. I mean, I can calculate this. I can show this, for instance, by calculate I can really look into the edge states, and they are there. So they are, in this sense, it's really like the churn number, okay? While I'm just saying, I can only give you a few examples where I can calculate this analytically, unlike the churn number. So that's the limitation, just because it's more complicated. But it works the same way.
And just another question, I think it actually might be related, because what's the magnetic characteristics of this bound flux around the vacancy? And how is it connected to this topological invariant?
That's what happens is the following. Because I mean, in the Kitaev model, you have to break your spin into Majorana and these fluxes. Okay, so that's how it operates, because it just break. And then in the Kitaev model, the flux state's fixed, which means you just need to find the ground state of the flux. I mean, you in principle can try all different ones. And what people realize, if removing an impurity, that would be the bound flux. So if you remove this impurity here, inside this plaquette, you kind of bind the flux inside it. So that's the ground state. So that's a kind of that's how fractionalized. Okay, so that's actually the ground state. So it's like the impurity is really binding a flux around it.
What is this flux?
It's
not a magnetic.
No, it's a flux in the U, in this let's say this gauge configuration of the Kitaev model.
What kind of information do you gain in terms of the magnetic order that is?
Oh, no, there's no magnetic order. It's just a spin liquid. What I gain is that because this bound flux, it makes let's say, the topological phase more stable. So that's the truth. No, but there is no magnetic order in here, okay?
Right.
No, it's just
Okay,
flux in this term of these U variables, okay? It's more abstract.
Yeah, very nice talk. I just have a quick question regarding the experiments on this thermal quantum Hall coefficient. In short, how do they know it is a Majorana chiral mode and not something else?
Oh, that's a good, because it's half. Because it's half. The half is everything. Because, I mean, if you have like a Fermi, it would be 1. I mean, this half, it would be really hard to get a half and a plateau if it's not Majorana. So you have to come up with a different view. The question is whether this is robust or not, and how this evolves with temperature, phonons are involved. There are several questions you can ask. But in principle, the half is the answer to your question. Because, I mean, this half here is really the central charge you would expect for the Majoranas. Okay, so that's essentially the reason. So that's why it's a strong signature, although it's really hard to measure and to interpret, but the half, essentially.
Thanks for the talk. I was just wondering if you have this realization for the monolayer or for the bulk, this alpha ruthenium chloride.
Oh, in principle, well, in principle, this, we are talking about weakly coupled layers. So interlayers are not so important for this field. Of course, they are there, but they are not relevant perturbation for this regime. Okay, although they can be there, they are relevant. But at least for these topological properties, they are not relevant because they're so weakly coupled.
I can find this for the monolayer and for the bulk.
Well, but the monolayer is trickier because then you have to have a substrate. Then the answer is I don't know, because I mean then the substrate could change. So the answer is I don't know because of that. People have tried to build ether structures. There's a whole new effort in this direction. But the answer will depend on which kind of ether structure you have. Okay, but
you can change the interactions, right?
Yeah, essentially, and also can distort and non-trivial. Yeah. So people, of course, are doing twisted and so, but the answer in this case is not as robust. It depends on which substrate we are using. But
I
people
see.
are doing this
I see.
just because, I mean, perturbation
And
become relevant.
do you know this, the strength of the magnetic field you need to get this spin liquid?
Oh, here, I know, I didn't show here. It's kind of 7K. It's basically the critical temperature. It's like 7 Tesla. It's showing here, essentially, 10 Tesla, like, depends on the direction. 10 Tesla, or if you go to 7 Tesla, you destroy, the plateau is like 10 Tesla. It's here, yeah. It's not too large.
Any more questions?
Oh, true. That's a good question. So in principle, you could say yes, but there's a caveat. So what would happen with the second spin liquid that should appear here, you would not be seeing it just because the U1 spin liquid at a finite temperature today it's unstable. But I mean, that's not a satisfactory answer. So at this point, we do not know. I mean, more studies. But if you're just thinking about this U1 spin liquid in 2 dimensions at finite temperature, it won't be stable. So it will be really adiabatic connected to the paramagnetic phase. Okay, so you won't see much of a signature just because the U1 spin liquid, this second one. But this is, as far as I'm aware, it's not fully established that it's a U1 because I mean, just have numerical evidence. So people still work on it. But that would be like naively how these things would fit together.
Okay, with that, let's thank Eric again. And the session is now closed. I'll just remind you